Hi again, welcome to the second part of my presentation on semi-device independent quantum random number generator based on the energy bound. In this presentation, I will describe the experimental implementation of the semi-device independent quantum random number generator described in the previous presentation with exploiting heterodyne detection. Note that both work can be found on arXiv with these two identifiers. Additionally, I will skip the introduction for this presentation as I already presented in the previous slide. So for more information on quantum random number generation and generators and introduction on randomness, please first watch the first presentation. Okay. This quantum random number generator is based on two-parameter measure scenario where there is a binary input to the transmitter and the measurement device outcomes a binary output. Having the input-output statistic, one can compute the experimental conditional probabilities. Inserting the experimental conditional probabilities together with the energy bound to the STP, side effect programming, which I described in the previous slides, one can compute the conditional entropy. Based on that conditional entropy, we can build our randomness extractor. And then by applying the randomness extractor on the low quality raw random bits, we can generate our final and private quantum random numbers. This is how this is the general framework of this protocol. The preparation is based on the binary phase shift keying or BPSK scheme. Depending on the input X, state alpha or minus alpha is transmitted. Note that the energy bound can be seen as this dotted circle. The state energy should be within this bound. It can fluctuate within this bound, but of course it cannot exceed the bound. Additionally, as mentioned earlier, the phase can fluctuate, but still everything should be within this energy bound. You might think that why we didn't use the overlap bound rather than the energy bound. That's because checking the overlap in a real experiment is not that straightforward and clear. On the opposite, the energy bound has a direct physical meaning and simply can be verified in a real experiment with the overmeter or simply a single photon detector. Moreover, the energy bound imposes a bound on the state overlap. Otherwise stated, when the mean photon number of the prepared state is upper bounded by a quantity, let's say mu, the scalar product of the state, which is actually the overlap of the state, is lower bounded by a value, which is 1 minus 2 mu. So in this way, we are sure that the state have non-zero overlap, thus they're non-orthogonal, leading to an inconclusive event, even with an ambiguous state discrimination or a UST measure. So we are sure about our randomness source when the energy of the state is upbound. In the previous presentation, I explained about heterodyne detection, and I told you that it gives information about both fit quadrature, let's say X and P. So the binary outcome can be estimated by dividing the phase space into two parts, let's say a positive and negative part. So if we get a click in this positive side or in this blue area, we assign the outcome to be 1 or p equal 1, otherwise p will be 0. Okay, let's talk more about data acquisition. We divide the collected signal into chunks of 1,000 samples. Then we calculate the centroid of these samples, as you can see with these two small crosses there. Well, we choose the chunk size to be 1,000 because it shows a great trade-off between the accuracy of centroid evaluation and phase stability. Indeed, each chunk lasts for around less than 1 microsecond, while the phase fluctuation is at the microsecond scale, as you can see in this figure. In this way, it is possible to determine the relative phase between signal and local oscillator. So by draw a line between these two centroids, we can find the relative phase and compensate for the phase shift. And finally, we apply a linear classifier, as you can see here, and then we assign the outcome to each event. If it's in the positive side, we say it is 1, otherwise we assign 0 to it. This is how we calculate the outcome. And also we have the input, so we can compute the conditional probability. Okay, the security estimation of this protocol is presented in the previous presentation file that is based on optimizing the guessing probability. So for more detail, first, please watch the first presentation. So optimizing the guessing probability is through the semi-definite programming. In the previous presentation, I just give information about primal semi-definite programming or primal STP code, while we can also the dual form of the STP code, which has some advantages over the primal form. So most importantly, the dual form, we can compute and take into account the finite size effect. And of course, it is much faster than the primal one. In addition, the dual form is linear in the conditional probabilities, and it gives us a reliable conditional mean entropy lower bound. The dual form is shown here, but I won't dig into detail, but I will be there to answer your possible question on this dual STP code. Okay, now it's time to address the experimental setup. The setup is made of two parts, preparation and measurement. Let's get started with the preparation. A continuous or CW laser emits light into 99 to 1 beam splitter. The lower arm, as you can see here, the lower arm is the signal, and the upper arm plays the local oscillator role. An FPGA at 1.25 gigahertz repetition rate derives the phase modulator, which is this one. Depending on the input, the phase modulator applies 0 or pi phase shift to the signal. In this way, we can generate alpha or minus alpha. The only trusted part of whole experiment is shown by this green box, which built from a variable optical attenuator, beam splitter, and the power meter. With this power meter, we can monitor the power of this experiment in real time, and if it's needed, attenuate the power with this variable optical attenuator. In the measurement side, the heterodyne detection is implemented through a 90-degree optical hybrid together with a pair of balance detector at 1.6 gigahertz bandwidth. The data acquisition is made with an oscilloscope with 10 gigahertz sampling rate, and then the data is transferred to a computer for post-processing and randomness extraction. It should be noted that we only use the commercially off-the-shelf component for this experiment. Okay. In this slide, you can see the experimental and theoretical result in a single figure. As you can see, the conditional entropy is plotted as a function of mean photon number. The orange curve, this one, shows the theoretical prediction without considering the losses. But as mentioned in the first presentation, this protocol is sensitive to the noise. So this green curve shows the theoretical prediction by considering the losses mainly coming from the detector efficiencies. And the experimental results are displayed by these dots here. As you can see, the experimental results are in great agreement with the theoretical prediction. Lastly, after randomness extraction, we could experimentally generate 113 megabits of secure quantum random bits, which is actually comparable with commercial quantum random number generators. By this, I can conclude my presentation. In these two presentations, we present a semi-DOS independent quantum random number generator protocol when the source is partially trusted, while the measurement part is completely untrusted. The protocol single assumption is bounding the energy of transmitted state, which we can verify in real time. The tight bound on the extractable entropy is obtained with STP, which represent both primal and dual form. And with dual form, we can also take into consideration the finite size correction. We experimentally implement this semi-DOS independent QRNG with BPSK modulation scheme and heterodyne detection in all-in-fiber setup with only using commercially off-the-shelf components. We use heterodyne detection, which allows for fast and which allows for fast generation with having a simple optical setup. Finally, we consider many outcome approach, allowing for more extraction with having the same experimental setup with only changing the post-processing scheme. Thank you for your attention.